this is no longer true. So the username Haxor isn't returned. So just verifying that. Order I1. Because in this case, obviously there is no table space name with a number of 1337. So if we then go back and modify that to say 4, which is a table space number that does exist, commit that, and then rerun the same query, we can see it's back again. Okay, so rather than modifying the text of the view, I mean, we can simply just manipulate the view itself so that it's disappeared. Now, I say this is a new method. It's not really new. This is exactly the same thing in Oracle that we did with XStatus in SQL Server. It's essentially abusing the view's content itself to make it, the account hidden. And of course, we can still use the underlying table user dollar to find user accounts. So it doesn't solve any problems as such. It's just, rather than changing the view of the text kind of thing, which is going to be easily noticeable, just modify do a direct manipulation of the data TS number, for example. Okay, modifying the binaries. From Alex's Oracle Rootkits 2.0, add the account, make a copy of the user table, and call it ASER, $, drop the account, stop the server, look for all occurrences of user $, and change it for ASER $, restart the server. Now all logins are now consequently read from this table. And so when the DBA looks at user $, instead he thinks, okay, I can't trust the view, so I'll look at user $, instead. The account is not visible. Well, there's a lot of hoops to jump through there, obviously. But one of the obvious reasons this will be easily spottable is the next time the DBA adds a new user account and does a regular check on user $, he'll be like, well, wait a minute, I just added an account. Where is that account? It's not showing in the user table. It sticks out like a sore thumb, as does the presence of a new data dictionary object, as does shutting down and restarting the database server. If your DBAs don't notice that, you should fire them and get new DBAs, kind of thing. And of course, we can check some of the OS files themselves. Again, improving the method, essentially the object here is to have a user account that's not visible from the user $ table. So can we do anything to achieve the same ends without actually having to modify the binary? Well, of course we can, otherwise I wouldn't be speaking about it. So if we, for example, do a create user Haxor2 identified by password, grant create session to Haxor2. If we then connect as Haxor2, and then reconnect as sysconnect, sysdba. If we then delete from user $where name equals Haxor2 0. Okay, one row deleted, commit that. Okay, now if we try and log, because we've essentially deleted that user, we've not dropped it, we've deleted the user, can we still log in with it? And of course, /password. So we've deleted that user, but we can still log in with it, essentially. So the thing is, if we then reconnect, or if we go select username from all users, order by 1, we can see that our Haxor account is in there, obviously, but our Haxor2 account isn't there. That's because we've deleted it from the sys sys.user $table. So essentially this achieves the same ends as modifying the binary. We hide the account from user $, but essentially this account is in the SGA. It's still in the SGA and available to be logged on because we've just done a direct delete from the user $table. So whilst it's more practical, because you obviously don't need to shut the server down and everything like that, the point is this will not survive a server restart. So the attacker needs to reinfect the server if it's ever stopped. But given that it's a database server and database servers are very rarely stopped, the user, or the attacker rather, has a good chance of their access being there for a long, long time. The way I see it, if you can modify a binary though, why not just patch the code so that if there's a user called, if someone attempts to log in with a username of Hags, or whether it exists or not, just log them in anyway, kind of thing. That to me is the easier way of doing it, because that way you don't have to create, arbitrary objects in the data dictionary. So, third generation rootkits. In-memory backdoors, basically, these are the things that Alexander, alluded to in his talk last year. So what are our options? Runtime patching of code. Well, Chris Anley did that kind of thing in 2002. So we won't repeat his efforts here, but we'll obviously talk about, at the end of that, looking at ways of, catching attempts to patch code at runtime. Obviously, we could change entries in the import address table. When an executable loads, or a DLL for that matter, and it requires to import functions from other DLLs, then the addresses are stored in what's known as the import address table. Now, and these are then dereferenced when they're called. So obviously, if we can manipulate these, we can redirect flow of execution. The other one, which is what we're mainly going to be concentrating on, is the manipulation of data. Data that is supposed to change, so in terms of watching for attacks against it, it's going to be much more difficult. Then we have to look at delivery mechanisms. How do we get our in-memory backdoor loaded? We'll look at external processes, network or libraries over the network, DLLs over the network. Or, for example, which is probably going to be the most easiest and most common attack, is either a buffer overflow, whether it be stack-based or heap-based, format string bug, or the kind of write a D word of your choosing to anywhere of your choosing kind of premise. So if we look at external processes as a delivery mechanism, we could use external procedures, for example. Call the system function to load an executable over the network. That executable would call open process on the Oracle process. Virtual allocx, this is obviously on Windows, by the way, if you're wondering. Call virtual allocx to allocate memory in the Oracle process. We need space for the stack and the code itself. We then write into the Oracle process using write process memory, and then create remote thread. But basically what we do is point the thread to the beginning of the code section. And then off it goes, and you can do whatever you want to do. You can do the same things, obviously. We can run executables from the Oracle JVM, but if we're running, the Oracle JVM is built into the Oracle process, by the way. So we'll look at, that's a bit redundant in a way, because, well, we'll come to that in a minute. We could call DBMS scheduler, or we can modify the PLSQL compiler flags. And the make utility, we can set that to an executable, and again, do the same things. Or we could load a DLL from the Oracle JVM, again, which, as I said, is internal. So this is why it's like, why do you need to load an executable just to achieve the same thing? Because we're already in the process anyway. We would call system.load, and it allows us to do whatever we want, obviously, once that DLL is loaded. So as a quick demonstration of this, this is just a simple DLL that exports, some functionality. It's a memory manipulator, basically, and a shell server. So once we're, have our requisite DBA privileges, basically, we can then essentially go around setting out, creating a Java class that will load a library for us. We then wrap a procedure around that and execute that. So this will load over the network. I'm hoping it will anyway. It might take a moment. Well, not might, it is taking a moment. Whilst that's going on in the background, I can't really talk about the next thing because until this demo's over. Come on. Yep, got an IP address. Oh, right, back in business. Okay, so PL SQL procedures successfully completed. If we then look at the DLLs list, DLLs, oracle.exe, we can see that it's loaded into the Oracle address space, the shell server listener.dll. Now, that there is its base address. So we can manipulate this contents of memory. So if we go star dump the next 10, oops, I need a host name, Apollo. So this basically, you know, takes an address and dumps memory from that, so we can inspect memory. This here is the beginning of the, you know, the DLL we've just loaded essentially, and this here is MZ and so on. You know, the PE header basically. So we can then change that if we wanted to. Not that this buys us anything, but we could change this to 41, 41, 41. So if we then look at that, we can see that we've written memory in the Oracle process essentially to 41, 41. Now what we could do is use this to cycle through memory looking for interesting things and change that to suitable values. Or to show you what else the shell server does, it's really crappy but a lot of fun. On port 1337 is a shell server essentially. So, you know, we can run commands and stuff like that. So that's all this DLL or backdoor does. It allows me to poke memory and connects me to a shell if I want it. Really crappy, but it does the job. Okay. Buffer overflows. Okay, these are probably going to be the simplest attack because obviously if there's if the remote Oracle server can get back out to me over, you know, the network, then there's real problems with egress filtering on the firewall. They shouldn't be able to do that. So in terms of delivery, if we can exploit a buffer overflow, we can pretty much load up everything we want from there. So the example we're going to show here is exploit a buffer overflow, an extant buffer overflow in Oracle. It looks for the password hash for the system user, and it does this by calling an Oracle function that essentially hands me back some user structures in the SGA, and once it's found the password hash for the system user, it changes it to a known hash that essentially is a password for secret. So the way it works is basically we need a handle to the SGA stuff first. Now these are hard-coded for this version of Oracle, but obviously you know, to make it useful across all versions of Oracle, then you need to avoid the hard-coded address problem. But essentially, we at this stage here, we've essentially got the handle to the beginning of the user structures, essentially. Once we've got that,